Alrighty. Welcome everyone to our Echidna workshop streaming series. So this is part two, where we'll be talking about fuzzing arithmetic functions and functions in general. So before we get started, just a couple of housekeeping items. So this is part two of our series. So you can clone the repo and open the part two folder. If you already have the repo cloned, go ahead and pull from the main branch. I just updated this stuff for part two, maybe like 45 minutes or 30 minutes ago. If you haven't watched part one, definitely give it a watch, especially if you don't know what Echidna is or don't know what property-based testing is, and this is your first time hearing about those concepts. Definitely a good starting point because we're going to build on top of that information in part two. Let's see what else. If you don't have time to clone it or are doing something else, this repo will be in the Critic GitHub organization, which is linked at the bottom of the screen. And then finally, this workshop, this session will probably be closer to 1.5 hours, just because we have a lot of ground to cover, and I want to make sure that everyone is set up properly for the remaining series or sessions. So this is part two. This is the workshop today. Part three will be next week on November 30th, which is a Wednesday at 12 p.m. Eastern time. And then parts four, five, and six will be in the subsequent weeks, and we'll remind you guys of those other parts next week as well. So just a quick reintroduction. My name is Anish Naik. I'm a security engineer at TrailofBits. I primarily focus on Ethereum smart contract security audits. I also help contribute to some of our tools and also do a lot of public speaking like this on Echidna, which is the topic of today. I work for TrailofBits, which is a security company that is research and development focused. And so, like I mentioned last time, what's really cool about TrailofBits is that we like to push the envelope in security. And one of the ways we do that is by developing a lot of open source tools that the industry can use. So a couple of those are Slither, Echidna, Tealer, Amarna, Solk Select. There's a bunch more. So definitely check those out. Again, all of them are the Critic GitHub organization, which you can find at the bottom of the screen. Okay, so today's agenda. We'll do a quick recap. So I kind of broke down this workshop into two sections, and they're sort of completely isolated pieces. But in section one, which was what we'll start with, we'll do a quick recap of what we talked about last week. We'll then talk about ABDKMath, which is sort of the math library we'll use to write function level arithmetic properties. Well, then we'll actually write them in the interactive section. And then we'll talk quickly about precision loss and the impact understanding precision loss has when you want to fuzz test something like ABDKMath, and also more generally when you're testing arithmetic operations, whether or not it's the library, it's still an important topic. And then section two, we'll do a hard pivot and we'll talk about two topics that are really, really, really important that will, one, set you guys up for the remaining portion of this workshop series, but then also that information should really give you almost everything you need to be able to go ahead and fuzz really anything you want out in the real world. So also really crucial section. Then we'll close up and then talk about what we have in store for the next workshop. So quick recap. So what did we talk about? We talked about a few different testing methodologies, and one of them was semi-automated analysis. And property-based testing is a semi-automated analysis technique that helps in identifying logical flaws in a code base. And additionally, it helps you find those hard to find bugs deep in the code base that may or may not be found through the other testing methodologies. Now, Echidna is one way you can do property-based fuzz testing. So Echidna is a smart contract fuzzer that will call a bunch of functions with a bunch of random inputs and test your target contract. And at the end of the sequence of functions it runs, it will go ahead and check the properties and make sure whether they're valid or invalid. And so properties can be thought of as truthy values or just Boolean statements. So it's something is greater than this, something is less than that. So properties help us describe expected system behavior. And so the goal really for this workshop and the rest of them is to figure out how do we define expected behavior for any system, a small one or a big one, and then how do we write those out in Solidity, and how do we test them with Echidna. And then at the end of last week, we talked about function level properties and system level properties. So we broke down this idea of properties into two categories. So function level properties exist at the function level. So they test one single function. The function can be stateless or be completely isolated, or just rely on a very small portion of the larger system. And so those become easier to test. And even on audits, we always start with function level properties before we get to system level properties, which usually require the deployment of the entire system and requires a deep understanding of how that system works. So similar to an audit, where we're doing fuzz testing, we'll have a similar journey during these workshops. So today we're going to focus on function level properties and talk about how to actually write those, and that's going to be the focus. And then in the upcoming workshops, we'll not only do function level property testing, but also look at some system level properties that exist for the different code bases that we'll be looking at. So how we're going to write function level properties is by focusing on this ABDKMath library. So ABDKMath is a library for fixed point arithmetic. And so fixed point integers or fixed point values help represent rational numbers. So the library has basic operations like addition and subtraction, and also has more complex operations like inverse, logarithm, power, natural log, and a bunch of other functions. So in Solidity, you don't really have this idea of rational numbers. You have whole numbers. You just have general integers. And what fixed point values allow you to do is you now can break down that whole number into sort of an integer part and a fractional part. So the integer part has a sign bit, which will determine whether the integer is positive or negative. You'll have the rest of the integer, and then you'll have the fractional part. So now you can define values like 5.4 or negative 34.6. That's the power of having fixed point representations in Solidity. So how does ABDKMath actually implement this in Solidity? So if we look at this sort of 128-bit length object here, the way ABDKMath does it is it treats this as a fraction. So it treats fixed point values as fractions. And the fractions numerator, the top part, is variable. It's this 128 bits that we have over here. And the denominator is an implicit 2 to the 64th. So it's dividing by 2 to the 64th. Now, when you divide something by 2 to the 64th, what happens is you get a left bit shift of 64 bits. And so now imagine before you had some value, let's say 100. There's this imaginary decimal right here, decimal point, dot, and then you'll have like a 0, let's just say. So 100.0. And now when you divide that by 2 to the 64th, you left shift this imaginary decimal point 64 bits over, and now you have the ability to not only represent the integer part of something, but also the fractional part of something. So ABDKMath works on these int 128 values, where the int 128 is actually the numerator of the fixed point value. And implicitly, when you're working with ABDKMath functions, the denominator part is taken into account when you do the operations. So that's why it's called 64 by 64 integers. 64 bits represent the integer part, and 64 bits represent the fractional part. Obviously, one of those bits is for the sign. Okay, so this is just a quick introduction on how you represent fixed point values in Solidity, or how ABDKMath specifically does it. It's not super relevant to the actual function properties we'll test, but it's something, if you want to continue learning how to test ABDKMath, this is something you should know. So that's why I just introduced this, but now we're going to kind of pivot into actually writing some properties. Okay, so what are the function level properties of ABDKMath? So the first thing to recognize when you're testing arithmetic operations is that when you test it, it doesn't make sense to re-implement the function that you're actually testing. So for example, if you're testing the addition function of the math library, it doesn't make sense to just redo all the steps of the math library. It doesn't say, okay, because I'm testing this implementation, thus the other implementation also works. So what we have to do is we have to go back to like algebra class or elementary school, wherever we learned this, where we have to test the properties of addition. So if we want to treat the addition function of ABDKMath just like any other addition function you would see on like the calculator on Wolfram Alpha, it has to follow these properties. It has to follow the associative property of addition, the commutative property of addition, or the fact that addition and subtraction are inverse operations. So I add y and then subtract y from x, I should get back x. Or if we're talking about subtraction, we can assert that subtraction is not commutative across the entire input space. So what we've done here is we've taken the operations, and now we're testing the properties of those mathematical operations, such as the associative property, commutative property, and so on. So now we're going to jump into a little bit of an interactive portion, and we're going to focus on two properties in this list. We're going to write out the associative property of addition, as well as this inverse operation aspect between addition and subtraction. Okay, so let's go ahead and write them. I'm going to check if there's any questions. Looks like we're good. Let's go ahead and write some properties. Okay, so to give you guys a lay of the land really quickly, so we're in the part 2 folder here. There's two subfolders. We have this ABDK part. So this is section 1, and this we'll focus on in section 2. So in section 1, we have the config file that we'll talk about in a second. We have the solution, which will be the sum of all the properties we'll write together in part 1. Template is what I'm going to work in right now, and then this is the actual ABDKMath library. Okay, so we're in the template file, and the file has a single contract called Echidna template. So let's walk through the file. We first have these wrapper functions, and these wrapper functions basically just call into the ABDKMath library. So for example, you can look at the subtraction function. It takes in 2 values, and really all it does is it returns the value of the subtraction function in the ABDKMath library. So again, you could use the using keyword using ABDKMath for int 128s. But again, we have these wrappers just for ease of use. So that's the first part of this. So I'm going to scroll past it. We then have these constants that are, again, useful for testing, but we won't really touch them for our use case. But again, if you do want to explore more, again, this whole repo is open source, so you can always use these constants. They will be useful for different types of properties. And then similarly, we have these helper functions that help with quantifying precision loss and identifying what precision loss is tolerable versus not tolerable. Now, we're not going to use it, again, provided to you guys just in case you want to explore more within the ABDKMath library. Okay, so let's actually write our properties. So we're going to first start with testing the associative property of addition. So note that we're taking in 3 parameters, x, y, and z. They're all free variables. That means Echidna will try to fuzz these values. So x, y, and z will be anything between the minimum of an int 128 and the maximum of an int 128. Okay, so first we're going to complete this side of the Boolean statement. So to honor the order of operations, we're first going to evaluate x plus y, and then we'll evaluate z. So we'll do int 128 xy is the addition of x and y. So we did the parentheses part. And then we can do xy plus z is the addition of xy and z. We honored the order of operations. We evaluated this first, and then we added this. Now let's do the same thing on this side, where we'll first do y plus z, and then we'll add x to it. So we'll do 128 yz is the addition of y and z. And then int 128 xyz is the addition of x to yz. Note again, we honored the order of operations here. Okay, so we have the left side done, the right side done, and now we're going to assert I want Echidna to prove me wrong or prove that I'm right, that the left side of this operation, x plus y, which is evaluated first plus z, is equal to the right side of the operation, x plus yz. Okay, and so that is our function level test. Note how straightforward it is to write function level tests for arithmetic operations like this, because it's completely stateless. We don't need to depend on anything outside of the addition function. And so we can just do the left side of this operation, the right side, and test this assertion. So recall that we talked about assertion mode last week. What we first started with when we were working with Echidna last week is we were using property mode. So in property mode, what we did is we wrote these kind of functions that look like function Echidna underscore something, no arguments, and it's a public function that returns a Boolean. So one of the big issues with property mode is that these functions can't take in arguments. That's something that Echidna requires, that these function hooks don't take in any arguments. And because you don't take in any arguments, you can't really do anything with the arguments. You can only really check state. You can't really take in arguments and use that to manipulate the state or to do some intermediate operations. And so the power of assertion mode, on the flip side, is that it can take in arguments. This is just a regular old function to Echidna or to the compiler is just a regular function. And the cool thing about it, or the thing that makes it unique, is that it has assertions. And because it has assertions, now you are in assertion mode, and you can actually try to violate or validate this assertion. So the question then arises, Anish, you mentioned last week that Echidna takes in 2 inputs. It takes in a target contract, and the second input are these properties like this. And how does that work with assertion mode? That's a great question. The answer for that is, in assertion mode, any public or external function is treated as the second input to Echidna. Now, Echidna will try to fuzz all those functions. It'll throw random inputs. If it takes in any input parameters, Echidna will fuzz those values, and it will run the function. And if there are assertions in that function, any public or external function in scope that have an assertion that fails, Echidna will let you know. So that when you go in assertion mode, anything that's public or external, Echidna now treats as its second input. So key difference, and that's sort of what also differentiates property mode from assertion mode. Okay, so just wanted to highlight that. We're going to be switching over to assertion mode. And note pretty much for the rest of these workshops and the rest of this workshop, we will be mostly focusing on assertion mode. Just because of this this is a big feature that we can get with assertion mode. Okay, let's run it. So we'll do Echidna test. And I'm going to tell Echidna to compile everything in template.sol. But I want my target contract, my input, to be Echidna template. And I'm going to provide it a configuration file. So another difference. Last week, when we wanted to use assertion mode, we did test mode assertion. Now let's say you have another configuration parameter, right? Echidna supports dozens of different configuration parameters. Let's say you have configuration X, and then Y, and then Z, and then A. So you'll notice that the CLI command is becoming incredibly verbose and very complicated. Now let's say you're working with some other developer or security engineer on your team, and they want to you have some failed tests and you want them to replicate it so that, like, as a sanity check. Now if they don't provide exactly the same arguments and they forget maybe the -a flag, now they're not working in the same environment. So how do you handle having a lot of different configuration parameters without bloating your CLI command? And so that's the use of configuration files. So the config file over here is the sum of all configuration parameters you would put in the CLI, but we'll pull all of them into a single config file. So it's just a YAML file. And here we're going to say that we're going to use assertion mode. And you can add all your configuration parameters in here. You can push this up to version control. And now everyone can use the same exact environment for fuzz testing. Okay, so the config file will be config.yaml. So that's how I specify the config file. So config and then the relative path to where the config file is. Let's run it. Okay, so the associative function test is running. It looks like it's running for a little bit. Great. Looks like we're not able to, looks like the addition function is complying with the associative property of addition. So can we make the conclusion that the addition function works as expected? Before we do that, I think a good idea would be to test another property of addition. And this time we're going to interweave subtraction into it. So let's do another property together. And in this one, we're going to test that adding y and then subtracting y gives you back the original x. So same pattern. Let's honor the order of operations. So I'll do x plus y is the addition of x and y. And then what I'm going to say, I'm going to create this value called new x, which is the subtraction of y from xy. And so this new x, our hope is that it's the same as the original x that was provided to this function by Echidna. And so I'm going to assert that the new x is the same as the original x. And there we go. That's the function level test to test that x plus y minus y gives you x. Okay, so with that in mind, let's run Echidna again. We can use the same exact command. We don't need anything different here. And now Echidna finds a failing property. It looks like this add sub inverse operations failed when run with Echidna, which means that this assertion was violated. So the call sequence that Echidna ran to violate the property that we care about is that it ran this function with 0 and 0. And somehow, when we did the addition of 0 and 0 and then the subtraction of 0 and 0, we did not get back 0. We got something that's non-zero because we know x is 0. That's what is provided here. But somehow new x is not. So what we could do is we could look at the addition function and then the subtraction function and say, okay, I figured out the root cause. But what if these functions are really complicated? So what we're going to do is we're going to take this opportunity to talk about one way of debugging your fuzz tests, and that's with the use of emitting events. So I'm going to switch back to my slide deck, and then I'll come back again in a second. So the problem statement here is, how do I identify why add sub inverse operations failed? So we're going to use event emissions. So emitting events aids in identifying the values that caused a property to fail. So if we go back to our VS Code here, we'll notice that we're doing a couple operations, right? We have these two input parameters. We do some manipulation here. and we do some manipulation here, and then we do the assertion. So how do I know what really failed here? I don't have any insight as to what the value of xy is or what the value of new x is. It's kind of like this black box. And what I want to do is get a lens into this box and say, what is actually happening under the hood? And that's what emitting events helps you to do. It helps you identify the intermediate states within a function, and that'll tell you exactly what's happening. And then you can maybe identify, okay, maybe the addition function is wrong, or maybe the subtraction function is wrong. And so that's the goal here. So at the top over here, we have this debug event that takes in two int 128 values. So that's what we're going to do. And we're going to emit some values. So we'll emit x and y first. We don't really have to, but we just will. And then we'll emit xy, so the first intermediate value over here, and then new x, the second intermediate value. And boom, we have, once these events emit, when we run Echidna again, we have the full picture of what's happening in this function. We have the input values, we have the first intermediate value, the second intermediate value, no other operations happen in between here, and now we have all the information necessary to check what happened before the assertion failed. So let's run Echidna again. Okay, so it failed again, as expected. But now we have an event sequence. In addition to the call sequence, we have the events that were emitted during that same sequence. So the first debug is 0 and 0. So those are the two inputs, right? So it failed on the same 0 and 0 input. That's what was provided. So that's the first debug statement. The second debug statement provides 1 for xy, and new x is 1. Okay, so now we know the value of xy is 1, and we know the value of new x is 1. So let's drill down a little bit further as to what happened. So when we added 0 and 0, somehow xy became 1. And then we did 1 minus 0 because y is 0 and xy is 1, and then we got 1 again. Okay, so it seems like the subtraction function seems to be working fine. We did 1 minus 0, that gives me 1. Great, I don't really see any problems with that right off the bat. But the addition function seems off. If I did 0 plus 0, I should get back 0, but instead xy was 1. And so because we used events, we were able to identify that there's more likely for there to be a problem with the addition function than the subtraction function. So let's actually go to the addition function in the ABDKMath library. And we'll notice that I introduced a little bug here, which is the regular added a +1 to kind of showcase the bug. So what are the two highlights from the two function level properties we wrote? One, when you're testing arithmetic properties, the addition operation has so many properties that arise out of it. The associative property, commutative property, a property like this where we use subtraction to test both subtraction and addition indirectly. So you can't just test the associative property and say the addition function worked. In fact, you could have tested the commutative property, which is x plus y equals y plus x, and that still wouldn't have triggered the bug that I had placed in the code. The reason we found it is because we had to take a slightly more creative approach to testing addition. So this again comes to the idea of what the human in the loop has to do. You have to get creative to identify the arithmetic operation you're testing and figure out what properties exist for that operation and how creative can you get when you test that operation. And then the second takeaway is using event emission. So with events, we were able to identify the entire intermediate state of all these different values like x, y, and new x. And then we got insight to be able to debug and say, I'm going to drill down into the addition function. I think there's a bug in there. So that's that. Those are the first two functions we wrote. Hopefully this provides a little bit of insight onto how to write function level tests and how to use events to debug. So I'm going to go back over to my slide deck. I'm going to take a water break and see if we have any questions. Okay, looks like we're good. Going to do a time check. Okay. So we're going to write one more property together. This one, we're going to do that division is not commutative. So we're going to check that xy does not equal y over x. So I'm going to go back to my VS Code now. I'm actually going to get rid of these two. We don't need them anymore. We did our job. Okay. We're going to test that division is not commutative. So same exact rodeo. We take xy, And we're going to first do the left side of this operation. So we're going to do int 128xy is dividing x by y, and then int 128yx is the division of y by x. And we're just going to assert that xy does not equal yx, right? That's what this Boolean statement is saying. And that's what we're going to assert here. This is the truth I want Echidna to validate or invalidate. Okay, looks good to me. Hopefully I didn't make any mistakes. Let's test it. Okay, Echidna says I did something wrong. What did I do wrong? So when Echidna passed in -1 and -1 to x and y, it looks like division is commutative. It seemed like xy and yx are the same. And that makes sense. You guys might have noticed this edge case too. -1 divided by -1 does equal -1 divided by -1. So in fact, it's not just when these values are equal, it's when the absolute values are equal will the commutative property actually hold for division. So that's an edge case. So how can we resolve this? We'll look at a few methods we can, few approaches we can take here. The first is we can add a precondition. So recall from last week, a precondition is something that bounds the input space or scopes the fuzzer to figure out its set of values that'll help you pass the precondition, right? So they're barriers of entry. And so the barrier of entry we're going to add is that I require that the absolute value of x does not equal the absolute value of y. And so whenever x and y, their absolute values are the same, you won't pass, Echidna won't be able to pass this precondition, and we won't test the property. Okay, so let's run it again. Hopefully this time, it doesn't break. And there we go. The precondition properly bounded the input space such that this assertion holds, assuming x and y, their absolute values are not the same. Okay, let's try something different. Let's say we do want to test this input, so we don't want to bound the input space. Now what do I do? So now we have to go back down here, and we can update our post conditions. So post conditions are the truths that arise from the action we take. And I'm going to define all these like things I've said over here, precondition and postcondition in a second. But we can update the assertions we actually test. So I can say if the absolute value of x does equal the absolute value of y, what I want you to do, I want you to assert that they are going to be the same. So xy does equal yx. So the commutative property does uphold for this edge case. Otherwise, assert this. And now we covered both edge cases, but not by bounding the input, but by updating our post conditions, or by updating the truths that we're testing. Let's run it again. And hopefully, note that I commented out the precondition. So again, both post conditions should be able to handle the entire input space. And it looks like Echidna is not able to find any set of values that can invalidate either of these properties. Okay, and so we've defined this word precondition. We have this word postcondition. And so what's the stuff in the middle? And so this stuff in the middle is what we call the action. And so now we have three keywords. We have the precondition, the action, and the postcondition. So I'm going to go back to my slide deck, and I'm going to define those a little bit more concretely. So this slide is all about structuring a function level invariant. So the precondition are the barriers of entry. So it says don't test this property unless these preconditions are true. So in our example, we did if the absolute values are the same, then don't test the property that I care about. Another example could be I require that mets.sender have a USDC balance before I do the action. And so what's the action? The action is what you are testing. And so the example that we had, it was dividing x by y and then y by x. Here, this example, the action could be transferring some to address some amount. And so notice what the precondition did when we're looking at the transfer function. If you don't have any tokens, the transfer doesn't really even make sense to try in the first place. And so that's the benefit of a precondition. You bound the input space. I don't care if you have no tokens, I don't care for you to try to transfer anything. If you do, though, let's go ahead and try to transfer. And once you transfer, I want you to check these truths. These are the outcome. This is the resultant state after the action is taken. And so the example, if we follow this train of thought here, the example could be the balance of mesh.sender for USDC should go down by amount because I have a non-zero token amount. I transfer some amount, and so my balance should decrease by that same amount. So that's the truth that arises from doing this action. Now, note that a little side note: when you do test post conditions, you should test both when the action succeeds, which is called the happy path, or when the action does not succeed, which is the not so happy path. And so it's very important to test both possibilities because that gives you complete coverage as to how your system is working. And one of the main ways you can do that is by using try-catch statements. And we won't worry about try-catch statements until the end of section 2. And so just keep that in the back of your mind. We'll come back to it. Okay, so let's go back here. And you guys will notice the same format. We have preconditions, we have the action, and then we have the post condition. So here, just to showcase that we want to use a precondition, this is the structure of our function level test. And I'm not kidding when I tell you that almost every single function level test I write will follow this exact same format. So keep this in mind, a very important takeaway from this section. Okay, I'm going to add one more twist to this, and hopefully this twist will make sense in a few minutes. So there's one issue with this precondition. It's fine, it does its job. But the issue is whenever this require statement fails, Echidna, the transaction that Echidna sends to diff test not commutative, the transaction reverts. And what that means is Echidna wasted computation because it was not able to solve this precondition. It was not able to provide me values that satisfy this precondition. So it basically wasted computation, and the computation didn't do anything. It didn't even test the action or the post conditions. So we can take a little bit of a different route here. And instead of a precondition, we can add something, an optimization. What I can do is if the absolute value of x is equal to the absolute value of y, I'm just going to make y 1 more than x. Now, this will only revert only if x is int 128, and then y will overflow, or the max of int 128, y will overflow. But every other time, no matter, even if they are the same or the absolute values are the same, then I'm just going to make y 1 greater than x, and I can still test my post conditions. So you'll notice this is how you can optimize your fuzzer. You can guide your fuzzer by making sure that you can do some arithmetic manipulation or use preconditions so that your fuzzer doesn't do useless work and it only does important work. So going back to my slide deck, this is the idea of optimizing your fuzzer performance. And so the goal when you optimize your fuzzer is to maximize the value of each transaction sequence that Echidna runs. So each time a require statement fails or an underflow or overflow occurs, that's wasted computation, right? We want Echidna to break assertions. We don't want it to fail because some require failed or some overflow or underflow occurred. We want it to break assertions or break properties. So notice that in this example, it doesn't really matter that optimization is not the end of the world. But if you're, when you're testing a real world code base with a bunch of different contracts, testing dozens of functions at once, if you fall into the same execution path that leads to the same overflow or same require failing, you're wasting a lot of time, and that makes your process slower and makes your life harder, realistically. So the solution to maximize the value of a transaction sequence is to bound your inputs with strong preconditions or arithmetic manipulation. So we looked at the example of a precondition in the last slide, which was requiring that the message.sender has a balance of USDC. Because, like I said, I don't care about trying to transfer more than 0 tokens. Or maybe the transfer function, it's a custom one that reverts if you try to transfer 0 tokens. And in that case, why am I even testing it in the first place? I know the transaction is going to revert. That's wasted computation. You could also use arithmetic manipulation like we just did. I said if the absolute values are the same, I want y to be just 1 more than x, and I can still test that division is not commutative. I could also use modular arithmetic, and we'll see this kind of example in the second section of this workshop, where if I do input value mod upper bound, the output range of a modular operation is 0 inclusive and upper bound non-inclusive. And so you can use this to access arrays. You can use this to bound amounts of token amount transfers. For example, going back to this, if I'm testing the transfer function, I don't want to try to transfer more than the user has. So I can do input value mod balance of message.sender, and at most that will be sent from Echidna is 1 minus whatever the balance of the message.sender is. So all three really important ways of bounding your inputs. We already saw how preconditions and arithmetic manipulation help us, and we'll look at how modular arithmetic can help us as well in the next section. Okay, so what are the key takeaways from everything we've done so far? So the first one is do not test arithmetic operations by redoing the operations. If you're testing addition, don't just re-implement the addition function. Test the properties that arise from addition, the commutative property, associative property, more creative ways. Note that we had to do something a little bit more creative than just testing the associative property to find the bug that I had added to the ABDKMath library. You can also use differential fuzz testing. So this is not something we'll talk about a lot, but I added a link at this specific line, and we have something in building secure contracts that showcases how you can use Echidna to differentially fuzz test contracts. So let's say, for example, in this context of arithmetic operations, you have this like hyper gas optimized assembly, arithmetic operation. What you can do is you could also write the non-assembly version of it that uses high-level solidity functions or in operations, and you can differentially fuzz them. And so what that means is what you're testing for is parity of execution. You want to make sure they both execute exactly the same way. So if the assembly version reverts on some input, so should the non-assembly version. And if the assembly version returns X for some input, so non-assembly version should also return X for that same input. And so that is testing parity in execution. And so that's the power of differential fuzz testing. So definitely also a really cool way of testing mathematical operations, especially ones that are written in assembly and are a little bit harder to reason through than just general solidity code. We then talked about emitting events and how that helps in debugging. So we used events to understand the intermediate state of our system right before the property failed, and that helped us drill down as to what was wrong, and it was actually the addition function that had a failing case or had a bug. And then most importantly, we talked about how to format function level properties. So we have preconditions, scopes the input, action, tests the input, and then postconditions are the truths that come out of the action. So remember this, very important. And you notice that this is quite similar to even how unit tests are run. You have preconditions, you got to do some setup, you send some tokens to X or Y, and then you actually call the function you're testing, and then you'll check the result of the thing you tested, right? But with fuzz testing or property-based testing, you have to get a little bit more abstract. You're not working with concrete values, you're working with just free variables that are manipulated in a variety of different ways. But same concept of precondition, action, postconditions. And then the last thing we talked about is optimizing your fuzzer runs with preconditions and arithmetic manipulations. We'll talk about this a little bit more in the second section, but very important, do not try to waste your fuzzer's performance. Make sure everything your fuzzer is doing is testing a new code path, not falling into the same traps. And the way you do that is by bounding your input space with preconditions and arithmetic manipulation. Okay, I'm going to pause again, water break, check for questions. Okay, so great question. How do I know that my tests are executing properly in assertion mode and that I'm not filtering every test? So looks like someone already answered it. We have Jocelyn and Nat again on Twitch and YouTube helping answer questions. But what a great segue. That's what we're going to talk about later in this workshop. So thanks for bringing it up. It's exactly what we're going to try to figure out. Okay. Okay. Also, apologies for I'm talking really fast. I know there's a lot to cover, so I just sped up a little bit, but I'll try to slow down. If you're watching me on 2x speed, good luck, I guess. Alrighty. So let's talk about precision loss very quickly. So precision loss is something that occurs when the value of an operation cannot be represented in the underlying data type. So one form of precision loss is overflows. So let's say you add 1 to uint256.max, then that value will overflow because 2 to the 256 cannot be held in a uint256. So that's just like a general form of precision loss that we see with regular numbers. With fixed point arithmetic, it's a little bit more nuanced because now you have this integer part and this fractional part. So the way you assess precision loss is a little bit different because not only can you overflow in the integer part, but you can also overflow on the fractional part. Let's say you need 66 bits to represent the fractional part, but ABDKMath is only scoped to an int 128. So only the first 64 bits will actually be contained in the int 128. The other 2 bits are lost. You lost precision because of that. So things like multiplication, division can all have variable amounts of precision loss. And the biggest reason for precision loss outside of overflows is because you're shifting bits. So you're literally moving bits from one place to another. And because you're moving things from one place to another, you might break out of the bounds of your data type. So how do you quantify precision loss? So various operations, like I said, have variable amounts of precision loss. So multiplication and division both can be kind of functionally proven to have uh, precision loss as a function of the magnitude of the two values that are being operated on. The inverse operation, the precision loss is logarithmic to the value of x. And the square root function, the precision loss is half the number of bits in x. And so I'm not going to explain as to the math behind it or the proofs that go behind finding all this stuff. But again, I have resources on the next slide that will provide a lot of insight as to where this comes from. And if you're curious about it, you can use this information to actually quantify precision loss in the ABDKMath library or any other math library in question. We also have some helper functions in solution.sol to quantify precision loss, such as equal within precision, equal within tolerance. So you can not only quantify it, but you can also make sure that after you've quantified it, I want to prove that my output is within 1% of my expected output, stuff like that. Okay, so here are the resources. Fixed point arithmetic and precision loss is not just something to worry about in Solidity. It's a thing that is a concern for embedded systems. Even calculators have to worry about it. Like, it's a big field of study. So here's some resources, and you can go ahead and check them out if you're more curious about this topic. Okay, time for a very hard pivot. So we're done with ABDK math. We talked about fuzzing arithmetic functions. If I really wanted to go deep into ABDK math, that would have been a whole other workshop to talk about all the different possible properties you can test. But now let's talk about two new topics: external testing versus internal testing, and coverage reports. The reason I'm talking about these two things now is because I want to make sure everyone is set up properly for the upcoming workshops, because we're going to build on top of this stuff. And two, because these two things will provide you the necessary information and guidance to be able to go ahead and actually fuzz almost any system out there. So that's sort of why I'm bringing it up now. It's a good stepping stone before we actually go into the remaining workshops. Okay, so external versus internal testing. I'm going to check for questions. Okay. So internal testing. So internal testing is the use of inheritance to test the target contract. So this is what we did last week. We had this test token contract, which inherited the token contract. Because we inherited the token contract, we got all the public functions, all the external functions, all the state of the target system, which was the token contract. And so because you inherited it, you are the target system. And so that's really powerful. And so that's the main benefit. You get the state of everything, and it's really easy to set up. It took me, a couple minutes to set up test token and just start testing properties immediately. The downside, or sorry, the additional benefit is that message.sender is preserved. I'll explain what that means in the next slide. The negatives, though, is it's not very good for complex systems, and it's mostly viable for single entry point systems. So let's say, for example, you're trying to fuzz test compound. You can't just inherit compound. Compound is a sum of multiple very complicated contracts. It has the C token, the comptroller, the unitroller. You can't just inherit the whole system. So how do you approach that? And so that's the downside of internal testing. It's really good for smaller, more isolated systems. But if you have a system that requires the communication of a bunch of different contracts, relies on a lot of different things, it's hard to do that with internal testing. It's not impossible, but it's definitely a little bit trickier. So this is how you can visualize internal testing. So you have this target system. This is from last week. The target system is test token, but since test token inherits token, you basically are targeting the system directly. And you inherited all the states and the functions. And now you have properties that you can immediately start testing right off the bat. And so this is what I mean by message.sender being preserved. So recall I said last week that Echidna is an EOA. It's just message.sender. So that was kind of a white lie. Echidna is not just one EOA. It's actually a combination of multiple addresses. So Echidna actually controls by default the 10,000, 20,000, and 30,000 hex addresses. So the reason why Echidna has 3 different addresses it uses to call the target system is because you can now emulate multiple senders. You can sort of mimic the real world a little bit, because realistically, there's not just one person calling these contracts. It's actually a lot of different people calling them. So now you can emulate multiple senders. Additionally, let's say there's a bug that can only be triggered if multiple people using the system. You now have a slightly higher probability of finding those kind of bugs because you have multiple senders. So this is what I mean by message.sender being preserved. The original Echidna senders are the ones calling the target system. So then what's external testing? So external testing is the use of external calls to the target system. So instead of inheriting the target system, you have this middleman, this like middle contract. and that's the one calling the target system. And what Echidna's mesh.sender is doing is calling the middleman. And I'll show that visually in the next slide. So the benefits of external systems or external testing is that it's good for complex systems with complex initializations and multi-entry point systems. So similarly, for example, again with Compound, you can use external testing with Compound because you can deploy the C tokens, deploy the comptroller, set up the comptroller so that it knows about all the C tokens in the markets, and you can do all of that using the middleman. And now you can test the whole system and all the properties that arise from all the different functions and the system level properties through this one middleman. And so this is actually what we mostly use in practice. This is on audits. I'm most likely going to be using external testing unless I just have like a single contract or something that I'm testing. The difficulty though is, or the cons is that it's slightly more difficult to set up. The reason being, setting up something like Compound is difficult, and that is the reason why we're using external testing in the first place. So that does add a level of complexity that complex initializations are just difficult inherently. And secondly, mesh.sender is not preserved. So again, what do I mean by not being preserved? So here's what external testing looks like. We have the middleman, this Echidna contract, and here's the target system. No, we're not inheriting anything. These are two isolated systems. So Echidna message.sender, the three senders Echidna controls by default, will call the middleman. So message.sender in Echidna contracts context is these guys. And now let's say the 10,000 address calls test fuzz with some fuzzed amount. The middleman is now the one communicating and calling the stake function in the token contract. So now Echidna contract is message.sender. So from the concept of the target system, there is only one message.sender. It's only Echidna contract. And so you're sort of indirectly fuzzing the target system because you take a fuzz value, you provide the same fuzz value to stake, and now you do something in the stake function. So there is a workaround. Let's say you do want to emulate multiple senders at this sort of barrier right here. You can, but it's sort of a discussion for next week. And so because we don't preserve message.sender, we do not emulate, we can't emulate multiple users, and thus we may not be able to find some kind of bug that could only be triggered if multiple users are using the system. But again, there is a workaround, and we'll talk about that next week. But suffice it to say, message.sender is not preserved. So again, the middleman is the target contract, which talks to the target system. So this is our first input to Echidna now. In external testing, this is our input, not this. Just keep that in mind. And when we look at the example in VS Code, hopefully all of this makes sense. Okay, another hard pivot. We're talking about something completely different now, coverage reports. We're going to merge these ideas when we look at the example. But I'm going to pause again, see if there's any questions, and do a quick water break. Okay, so looks like there was a question. It seems like it was answered. I don't think I have anything to add to that. But the question was, if the function of the smart contract we try to fuzz calls arbitrary external code during the action, does that make sense to fuzz? And the answer that was provided is Echidna will use existing contract addresses for the address parameter, so the callback can reach one of them. Otherwise, you will need to guide the callback. Yeah, it's actually a really great question. And yeah, like whoever answered, we have an exercise related to that in building secure contracts. Actually, the next I think 5, 6, and 7, and we might be adding 8. All are about using flash loans, and flash loans are one example of having callbacks. So I would definitely, whoever asked that question, I would definitely go check those out. They're good examples. Okay, all right, let's keep going. Coverage reports. Time check. All right. So what is coverage before we talk about the report part of it? So coverage is the tracking of what code was touched by the fuzzer. And so this actually applies to any general testing utility. So Hardhat has a concept of coverage. When you ask for what's my unit test coverage, Hardhat will tell you, hey, Anish, your unit test covered 70% of this contract and 30% of this contract. So Echidna similarly has the same concept of coverage. And so it has this internal way of tracking what parts of the code were touched and what parts of the code were not touched. And so the report is the output of that. That's Echidna's report to you to say, Anish, I covered these parts, this part of the code, and these parts I did not, maybe. And so the report actually is a .txt file with all the target source code. So it's basically, if you have 20 contracts in your project, it'll flatten all of that into a single text file. And each line in the report, which each line is an operation or it does something, right? It's Solidity code. So each line in this report is marked either with a star, R, O, E, or none of the above. So starting with none of the above, if you don't see any 4 of these symbols next to a line in your report, that means the line was not covered. Echidna, over its 50,000 iterations, 100,000 iterations, never touched that line. Okay, so what do the other 4 symbols mean? So a star means that at some point this line was executed with no errors. What that means is, again, Echidna is running 50,000 times. So let's say on iteration number 1, you ran a line and that line ran successfully and that line did not revert. The execution ended with a stop, and that line worked out perfectly. There were no reverts. Similarly, R means the execution ended with a revert. So that means, let's say on iteration number 2 in the 50,000, Echidna runs the same line or a different line, and that caused the transaction to revert. That line will be marked with an R. Same argument with O, out of gas. So this is common with loops. And then E is execution ended with any other type of error, such as zero division, overflows, or anything like that. So in practice, really, and the ones we'll talk about today are the star and the R. So those are the ones that you're more likely to see. And so note that star and R are completely mutually exclusive, because like I said, I highlight here at some point. So when Echidna runs 50,000 times, if in execution or iteration number 1, some line has a star next to it, that's great. But if in execution number 2, that same line reverts for some reason, then that line will also have an R next to it. So you can have a star and an R at the same line. And when we look at the example, hopefully that makes a little bit more sense. So again, mutually exclusive. Star means one thing, R means something else. Together, they don't really mean anything special, but each individually means something different. Okay. I know it's getting a little, hopefully it's not too convoluted, but we'll look at the example real quick. So before we do that, why do we care about coverage reports? It is your best friend when it comes to Echidna. If you take away only one thing from this whole workshop, it's use coverage every single time you run Echidna. So it's 2 benefits. One, it's a crucial debugging tool because it'll tell you whether your assertion tests are wrong, whether they're working properly. And so this is going back to the question that someone asked in the chat. So it's a great debugging tool, and this is how you should use Echidna, with coverage enabled every single time. And it provides you a guarantee that your test ran as expected. And it also provides you a guarantee as to what parts of the line or what parts of the code were covered. So if you're fuzzing a function, the hope is by the time Echidna finishes running that you have tested every single line in that function and every possible conditional or branch that function takes. And that would be considered full coverage of that function. So how do you run Echidna with coverage? So if you're using the CLI, you have to provide a directory for the reports to show up. So you do corpus dir and the name of the directory. So the directory will hold the coverage reports at the end. After Echidna exits, Echidna will populate a new file with the report, a new text file, which will be the report for that sequence of runs. If you're using the config file, which is what we'll do, we'll actually set corpus dir and the name of the directory. Okay, enough talk. Let's look at an example. So we're going to look at this staker contract. It's a simple staking system. And what we'll do is we're going to have 2 goals. Are we actually testing the properties we think we're testing? And does the coverage report provide any insights as to whether or not we're testing the things we think we are testing? Okay. Moving back to VS Code. Let's close these guys out. So this was the ABDK part. So I'm going to open the staker contract, the template for this part, the config for this part. Okay, so in the config file, we'll notice that we've set the coverage on, right? So, and you see how simple it is. I don't have to ever worry about consistently adding this to my CLI every single time, because sometimes, when I was first starting to use Echidna, I would forget all the time. But now, since I have a config file, boom, I can never forget. It's tracked here. Okay, so let's start with the staker contract. The staker contract has the staked balance mapping that holds the staked balance of a user. We have this token to stake. That is actually the token that will be transferred to and from this contract. So if you stake some amount of token to stake, then your stake balance increases. If you unstake some token to stake, that token to stake is transferred to you, and your stake balance decreases. Pretty straightforward. So your constructor, you taken the token to stake address, then you set it to this token to stake parameter, or token to stake state variable. Okay, so the stake function takes an amount. And what it will do is it'll first transfer that amount from mets.sender to this address. And then the amount of your stake balance increases by exactly how much you sent in. So your staked amount is exactly how much ever you sent in. Just the exchange rate is 1-to-1. There's no, interest or yield or anything like that. We're keeping it very simple. And then we update the balance of the sender. So the stake balance of mesh.sender increases by how much ever you transferred, which is exactly how much you stake, which is exactly how much your balance goes up by. Unstake does the opposite. So we'll check that the mesh.sender has a balance more than or equal to how much ever you're trying to unstake, so that we prevent an underflow here. So now we'll update the balance to assuming that you have enough stake balance. You'll decrement your balance, and the amount you get transferred is exactly how much you unstake, which is why the amount is set as staked amount. And then we'll transfer to mesh.sender that amount. And that's it. Straightforward. We have two functions. And what we're going to do is we're going to write two function level property tests for these two functions. So the template file here has this Echidna template contract. And so notice right off the bat, we are not inheriting Staker. We are a completely separate system from Staker. We are not Staker. We are Echidna template. And so this is external testing methodology. And so because we are a completely isolated system, we have to deploy the system ourselves. So we have to actually deploy the Staker. We have to actually deploy the token to stake and set up our system accordingly. So in the setup function, what we'll do is we'll create this new token to stake, and we'll use this mock ERC20, which is up here an ERC20, but it has some additional tricks up its sleeve, but we won't talk about it right now. We'll talk about it in a little bit. But just know it's an ERC20. It's the same exact thing. So we deploy an ERC20 contract, and then we create a new staker contract that takes in the address of this token. So great. We deploy the token, and we created a staker, and we gave it the address of the token that we just deployed. So that's the setup. Remember, you have the inputs that Echidna needs, and then you have a setup aspect, right? So those are the things you have to worry about every time you use Echidna. And now we have our function level invariance. So we have test stake, and you'll notice that we're starting to see this pattern come again: precondition, action, postcondition. And let's walk through that. So we take in a fuzzed amount, so it just is any value between 0 and UN256.max, and the precondition checks that this address has some balance of token to stake. And so notice here, we're not doing mesh.sender, we're doing this address. Because remember, this address is the one that's actually talking to staker.sol, not Echidna's mesh.sender, it's this address. So what I really care about is whether this address has tokens or not. So I'm requiring that this token has some balance, or this address has some tokens to stake in the first place. And if you pass that, then we're going to do an optimization. We're going to use modular arithmetic to bound amount to be between 1 and the balance of this address. Because again, I know if I do something more than this address has, the transfer from here is going to fail. You can't transfer more than you have. And so why would I even try that in the first place? That's wasted computation. So I'm going to make my lower bound 1. And then because of how modular arithmetic works, the upper bound will be balance of this address, and the lower bound will be 1, both inclusive. So I can do as little as 1 and as much as everything I own. And then I take the state before the action. So I'm caching my state here. So I'm getting my current staker balance. And the reason I do this is twofold. One, it helps me with emitting events. So let's say I crash the function and there's some problem. I can emit an event and see what these actual values are when the test fails, and that might provide me more insight as to what's going on. It also helps me by post conditions, because I can use that to actually test that my staked balance increased. So that's what I'm going to do. I'm going to take my action. I'm going to actually stake how much ever this optimized amount is, which is bounded between 1 and the balance of this address. And then the post condition will check that my new staked balance is my previous staked balance plus the amount that I staked. Note that the stake function returns how much ever you staked, which should be the same as the amount. So I'm just making sure that my balance increased exactly how much I think it should increase by. The unstake function does something similar. It takes in a staked amount, and now the precondition is different. I am requiring that my stake balance is non-zero. So again, there's no reason to unstake if I don't have staked tokens in the first place. So I'm going to make sure I have some tokens to unstake before I even continue doing the rest of this function. So I do that, and then I have an optimization, which is I'm going to bound how much I unstake between 1 and the balance of this address, similar to that one. There's no reason to unstake more than you have. We know that's going to fail, and there's no reason to really unstake 0. And then we take the state before the action, we cache that. We take the action, we unstake. And the post condition we check is that my new token balance of this address is my previous token balance plus what I expect to have been transferred after I unstake the amount of tokens I wanted to unstake. I want to note here that there's additional post conditions you can write, like there's additional truths that come out of this action. For example, my token balance, the token balance of address of this should decrease. The token balance of the staker contract should increase. So there's a bunch of different post conditions, but for the sake of this example, we're just going to test this one post condition. Okay, so that's the lay of the land. I guess I actually didn't give the lay of the land, but the staker subfolder within part 2 basically it's a hard hat project. So we have the config file here. We have this contract subdirectory, which has the staker contract. That's the actual target system. Template is what I'm working in, and solution is the solution that we'll work towards right now. Am I missing anything? No. Okay. All right, let's run Echidna. Okay, so Echidna test. And this time I'm going to tell Echidna to compile everything in this project. So this is different than what we've been doing previously. And the reason we have to do a dot, which means compile everything in this project, is because we now have external dependencies to third-party libraries. And we have to depend on these, and we have to be able to import them and compile them accordingly. And Echidna, just by compiling Echidna template or everything in this file, that has no idea what the heck I mean by Open Zeppelin contracts token, whatever, right? It's not something in the local directory. It's a third-party dependency. And so now, because Echidna will internally depend on critic compile, which will then handle using hard hat for compilation, you're basically saying Echidna will compile this project exactly how this project would be compiled by default. So we're compiling this entire project, and then I still have to provide its first input, which will be Echidna template. So this is the target system. Note that this is the middleman, but this is what Echidna will be calling. And the Echidna template, the middleman, is the one that's actually communicating with staker.sol, or the staker contract. And then the config file is config.yaml. Remember that we've enabled coverage. Okay, so we're running. Seems to be no problems. Test take and test untake are both working. And it does not look like there's any problems with our properties that we're testing. Okay, does that mean we're good? Before I make that claim, the first thing I will always do, let's say this is a real audit, the first thing I'm going to do is I'm going to go check my coverage. So you'll notice that in this same staker subdirectory, we now have this corpus folder that's been populated. And this corpus folder has now this coverage subfolder, which are interesting sequences that that Echidna will kind of store on the local file system so that it can reuse it in later runs. And then we have this covered file, which is the actual coverage report. So coverage reports look like covered dot timestamp or some number dot txt. So we'll open this up. And so this is the flattened file with all the different contracts. Okay, so what I care about is I want to see what my test stake function looks like. Okay, so this is my test stake function. Not looking very good. We have no coverage here. So the line annotations will show up here right before this delimiter. And I have absolutely no coverage here. I'm not even testing my action. Heck, I'm not even getting to my post condition. I'm really just getting stuck at this precondition. It seems like this address doesn't have a balance of tokens. And that makes sense because I never minted this address any tokens. And so immediately you can see the power of coverage. Because if I just ran it like this, I could have made the claim we passed. We tested our assertions. Nothing wrong with your code. Good job, client. You did a great job. But realistically, I don't even know if they did a good job. I didn't even test the property in the first place. So I need to mint some tokens to this address. Okay, and now we're going to circle back to the mock ERC20 contract. So this, again, highlights the power of inheritance, like I mentioned last week. What I'm doing is I'm taking the ERC20 system. I'm inheriting it into this mock ERC20 system. And what I'm doing is I'm adding a public mint function. The regular ERC20 system does not have a public mint function. So how am I to provide Echidna with any tokens if there's no way to mint tokens? And so this is how you can use inheritance to create custom behavior for whatever you're doing. So for example, if you have to somehow emulate an off-chain oracle, you can create a mock oracle. And you can have some functions in there that would provide some fake data, but now you have something to actually work with, and Echidna can rely on that as its quote unquote oracle. So mock ERC20, mock Oracle, mock whatever, really, really valuable for doing fuzz testing. So just keep that in mind. So this mint function is now public, and so I can actually use it. So I can say, token to stake, mint this address, a whole bunch of tokens. So I'm going to provide it uint128.max. So I'm going to give it a lot of tokens. All right. Now let's see what happens. So now I firmly believe I did my job. I should be able to get good coverage. Okay, looking good. Still not crashing. Our properties look fine and dandy. Let's go see what our coverage report tells us about it. So as you keep running, more coverage files will show up here. The last one in this directory will be the latest coverage report. Okay, so we're going to go back to our test stake function. Okay, so we made some progress. Our annotations have extended further down, but now we get stuck here. We're still seeing no stars. Not good. And we're seeing that this action fails. When we call the stake function in the staker system, it fails. Okay, and I get no coverage after this, so there must be something wrong at this line, at this in the stake function. So let's go check out the stake function. And here also, not looking good, no coverage over here. We keep getting stuck on this transfer from. So when I transfer from mesh.sender to this address, looks like there's some problems. And naturally, the problem is we didn't provide any allowance. The template contract did not give the staker contract any allowance to be able to perform the transfer from properly. So there's two ways we can handle this. We could technically add the allowance here. But what we can also do is we are going to look at something we call function overriding. So what I'm going to do is I'm going to write my own transfer from function. And now because token to stake is in mock ERC20, it'll use this transfer from function. I've overridden ERC20's base implementation of the transfer from function. And because I did that, I can write whatever I want in here. And so what I'm doing is I'm disabling the allowance check. And boom, I don't have to worry about allowances anymore. And so this is something we'll commonly do. I'm not saying, by the way, that always disable allowances, but it's a good way to just bypass it. It's not something we're worrying about, right? Again, we define what we care about. I'm saying I don't really care about allowances right now. I just want to move forward. I just want to test the staking system. I know that the allowances for an ERC20 work as expected. So I'm going to comment this out. I've overridden the transfer from function, and I can go ahead and keep testing. So again, function overriding, inheritance, all very important. We're starting to see these patterns continue showing up. Okay, so we've disabled it. Now I pray that it works. Okay, looking good. Property not violated. Echidna's doing a good job. All right, let's see if our coverage says that I'm doing a good job or not. Here's coverage file. Actually, you want to look at the test stake function first. Okay, look at that. Stars everywhere, gold stars to everyone. We did it. We have no reverts anywhere over here. We passed the preconditions. We're able to do the action. We're able to test the post condition. Star is good. We didn't fail. We test the assertion, and in the how many ever iterations we ran, 2,170 iterations, not even once were we able to break the assertion. That's great. So let's see what our coverage looks like for the actual action. Let's go look at the stake function. So stake function also has a lot of coverage. We covered every single line and nothing ever reverted. And so again, you see the value of the coverage reports. I was able to debug through the mistakes I made, and then I'm able to also provide a guarantee as to whether or not I got full coverage of the stake function. Okay, test unstake function. Also looking very good. Great. We go to the post condition, we're testing it, and we're seeing this little R over here. And so at some point, Echidna was able to pass it, but at some point, Echidna was not able to have a staked balance because that's the precondition, right? You need to have a staked balance. And this is the power of what we call stateful testing. So remember, I mentioned last week that Echidna calls a sequence of transactions or a sequence of functions. And while it's doing this, it's maintaining state. It's maintaining the state database of the EVM. And so the power that provides us is that we don't have to explicitly call stake in here. I don't have to call stake and then test the properties of stake and then call test unstake or then unstake the tokens. I can just assert, or I can require that Echidna needs to somehow figure out a way to get a staked balance before it tests the unstaked capability. And so Echidna, because it can call a sequence of functions, it will call test stake first. And because now, if it passes, it'll have a staked balance, it can call test unstake, pass the precondition, and then do the rest of the stuff. And so using preconditions to guide your fuzzer really helps make it really makes is what makes Echidna powerful and helps makes your tests modular. If you're testing function z and function z relies that you call x and y before, it doesn't make sense in testing function z that you call x, call y, test y, and then call z and test z. You can have required statements or preconditions where you can define that, hey, I need Echidna to first call x and y, only then can you actually do the stuff in function z. So really powerful. Should be another big takeaway from this discussion. Stateful testing allows you to create really nice and flexible function level tests. I never had to call stake in here. Echidna just had to call test stake and test unstake in sequence to be able to do it. And again, there's only two functions. The probability is pretty high that Echidna will try a sequence where test stake and then test unstake are called in order. Okay, deep breath. Let's keep going. Last thing I want to highlight here is try-catch closures. So I mentioned earlier about testing both the happy path and the not so happy path. So here the issue is the staked when we call stake, if stake reverts, I will never test my post condition. So if I go down the unhappy path of this reverting, I'll never know. I'll have no idea whether or not this ever fails in the first place. I only test the happy path right now. So try catch closures can help us test both paths. So I'm just going to copy it for the sake of time. All right, try catch, bang. So our action is still here. The action is this part, but now we have the post condition checks if the action succeeds and if the action fails. So let's see what power this provides me. So in the successful case, I'm going to test what I was originally testing. I'm asserting that my stake balance is increased. And I firmly believe at this point that there's no way for this to fail. I don't ever believe that an unhappy path exists if I'm calling the stake function. So if I ever fail, if I ever catch an error, I'll assert false, which means we failed our property. There's something wrong, Armageddon. Let's go check it out. Now, what I'm going to do to kind of highlight the benefit of this is I'm going to get rid of my overridden transfer from function. Right? So we're going to have this allowance problem again. But look what the difference, look, we'll see what the difference now. Note the first time, Echidna did not crash. Echidna did not say we failed the property. But let's see what happens when we use a try-catch closure. Now Echidna fails. It says, Anish, like, I tried. You're telling me to assert false if it fails. I am. And now we also get an event sequence because the ERC20 contracts will emit an event if you have an insufficient allowance. I know exactly why I failed to run my properties is because I didn't provide an allowance to the staker system. And great, now we have two ways of sort of debugging here. We have coverage reports as well as using try-catch to kind of drill down into why am I failing? Am I failing for the right reasons? If I'm not failing for the right reasons, then maybe I need to update my preconditions or change my setup. If I am failing for the right reasons, that's great. Maybe sometimes the function should fail, right? It's not always that the function has to succeed. Okay, so we did a lot here. We covered a lot of ground with this example. So first, we started with external testing. We looked at how external testing is a different methodology than what we've done previously. With external testing, we have to deploy the system ourselves, but it gives us a little bit more control and gives us the full scope of the system. But the downside is the message.sender is no longer Echidna's 3 message.senders. It's actually this single target contract. We then looked at how to follow the pattern of function level tests again. So this is again precondition, optimization, action, postcondition, same thing that we saw earlier. We then looked at how coverage reports helped us debug and find the mistakes that we made where we forgot to mint some tokens and we forgot to provide the allowances necessary. Then we also looked at how we can use stateful testing and make our test really modular because I don't have to call stake in here. Echidna will call stuff in sequence and figure out that once it calls stake and then it calls unstake, it gets more coverage. And so that's pretty interesting. So I'll keep doing that and I can keep going deeper into this function. And then we finally touched upon try catch closures being really beneficial in testing both the happy path and the not so happy path. Okay, let's wrap up here. Let's see, question check. Great question. So I explicitly made Echidna mint tokens. We could do this as well. I'm not going to run it, but I could also have this function. So sorry, the question is, I didn't say the question. Could Echidna eventually figure out to mint tokens the testing contract after a long enough time? So because the mint function is not public, because the underscore mint function is not public, it can't. But you have to first supplement the mock ERC20 with the public mint function. And instead of explicitly minting it, what I can do is, let me add the transfer from back so we can actually run this. What am I doing? Yeah. So we can do test mint, and we can take in an address, 2, and a amount, or UN256 amount. And now what we can do here is we can say, if you call the test mint function, Echidna, I'll mint whatever address you specify, how many ever tokens you want. There you go. And so now now this is actually something I'll do on audits actually. The explicit mint is fine, and sometimes it's totally okay to do that. But you can also, again, we're doing stateful testing. Echidna will get stuck here. So say, okay, I'm going to try something else. What if I call test mint where address 2 is my own address or the address of this contract? Okay, now I minted myself some tokens. And now if I go back to test stake, oh, I can pass this. And great, I can continue doing it. And so this is exactly how you can help Echidna figure it out without a guiding hand where you provided a public function to hit, and without having some kind of function to call. Echidna won't be able to figure it out. But now you've provided Echidna the ability, an entry point to be able to mint functions without you explicitly doing it. Note, I'm not doing it in the constructor. It's just a function. Echidna can choose to call it or not call it. But obviously, Echidna at some point will call it, mint itself some tokens, and then actually go ahead and stake and unstake. Okay. Do we have some way, another question, do we have some way to erase the revert message directly without try catch? Yes, you could do like a low level call. So this is another way, and we'll actually use low level calls next week. So I guess this is a good precursor. So you could do something like address staker contract dot call, and then you could do or sorry, whoops. Yeah, you could use that. You can do dot call and say address staker contract, and then you can ABI encode the function selector, or we can do ABI encode with selector. And it could be the staker contract dot stake. I'm not going to write this all out, but the point is, a low-level call like this will return 2 things. It'll return a success and an error, a bytes memory error. And now you can assert on the success, or you can do if success, do one thing. So this is the happy path, else do something else. And this is the unhappy path. And so that's another way you can test for both happy and not so happy path by making low level calls, because you actually get the success parameter, which will tell you whether or not the function ran as expected. Okay, hopefully that answered that. Do you have to worry about the 6364 gas issue when using the try catch here? Like not really, because when you're doing try catches here, you're 99% of the time, I don't think I ever have really called an external function in here. I'm just mostly doing simple assertion checks. And so it's not something I've had to particularly worry about when using try catch closures, because I'm not making external calls in here. I'm just asserting a bunch of Boolean statements, and same with the catch closure. So yeah, that's not something you will have to particularly worry about. And know that you can control how much gas Echidna uses per transaction. So if you feel like if you start getting out of gases and you see that in your coverage, you can just up the gas and see whether that helps. And if it doesn't, looks like there's some computation that's really heavy, and that could be an execution path. That could be an actual bug. Maybe it's a for loop that's really long or something. So, but no, I haven't had to deal with that specific edge case, the 63/64 gas problem with try catch closures. Okay, barring any other questions, let's conclude. All right, so what are the key takeaways from this lecture workshop? We talked about how to write functional level properties. So this is a big takeaway. Precondition, action, postcondition. Always remember this. Bound your input if you need to. Take the action you want to test, and then check the postconditions that come from doing the action. Don't forget about rounding errors when testing arithmetic operations. This applies to not just fixed point values, but just general arithmetic. So I'll face this a lot. I'm in an audit, and the code is like doing a lot of divisions. And now, if you had full precision, you could do x equals y. But let's say y rounds down significantly, I can no longer have such a strict assertion. I would have to maybe do x is greater than or equal to y, or x is less than or equal to y. Or if I want to be even more advanced about it, I could say x and y are within 0.1% or 1% of each other. And so rounding is always a big factor when you're fuzz testing arithmetic operations. So keep that in mind. Test optimization can be done with preconditions and arithmetic manipulation. So we saw 3 ways of doing optimization. Preconditions can bound the fuzzer and make it stop it from doing useless work. Arithmetic manipulation can do the same thing. You can do arithmetic manipulation like we did with our division example, or we can use modular arithmetic. Modular arithmetic is actually very common, and we use it all the time in our audits. Debugging, we looked at events, helping us identify the intermediate state of your system when you're writing fuzz tests. We looked at coverage reports. Remember, coverage reports are your best friends. Please do not run Echidna without coverage reports, especially if you're doing something kind of advanced. It is a waste of your time. Check it every single time you run Echidna and you Control-C Echidna. Go check your coverage report. Go get some confidence about what you're doing. And then we talked about internal versus external testing and how external testing is what we use more in practice. And we'll see this sort of play more in the future workshops. Note that we could have done that example with internal testing as well. I won't show it to you guys, but both could have been done. But again, with more complex systems, external testing is actually the one that's used more. In fact, actually, we can actually combine both methodologies, and that's a spoiler for parts 5 and 6. Okay, your homework assignment from similar to last week. Continue writing properties for ABDKMath. We can get a lot more fancy. The ones we did were pretty simple. Associated property multiplication, distributed property, multiplication of inverses, square roots, logarithms. Note that almost all of these will have precision loss. And so really the challenge here is you can obviously loosen your assertions and say they're approximately equal, but it would be way cooler if you can precisely say, I expect exactly this much precision to be lost when I'm testing the associated property multiplication, and use that as a property. And so all these properties have actually already, like one of our apprentices, Guillermo, absolute machine, wrote a huge number of properties for ABDKMath. And so we're actually going to open source those properties in critic / properties. So properties will be the actual repo name. It's not open source yet. It's still closed source. We're working on it, but just keep that in the back of your mind. You can always find it. You can always add alerts for any updates to the critic organization, so you can always find out when those come live. There's a lot of cool stuff that Guillermo did. So definitely check it out when it comes out live. All right, last thing, next streaming session will be on part 3, November 30th. So next Wednesday at 12 p.m. Eastern time. We're going to take it up a notch. We're going to start talking about real world code bases. So we're going to look at properties of AMMs and specifically Uniswap v2. So a lot of fun stuff coming up. I'm really happy with all the feedback I've gotten about from the previous workshop. And thank you to everyone who watched the last one and is watching this one or will watch this one. We really love it. We love that people are enjoying this stuff and providing feedback. So super excited for the future workshops. Don't forget, next November 30th, next Wednesday at 12 p.m. Eastern time. Okay, this is the last time you guys will be seeing me. Thank you everyone for watching again. Yeah, that's it. See you guys.